Hello, welcome to The Naked Scientists with me, Chris Smith, and also with Ginny Smith.
This week, mass extinction. 250 million years ago, nearly all life on Earth ended. Back from the brink, history then repeated itself with the disappearance of the dinosaurs 60 million years ago. Are we next?
Let's hope not, but we'll find out. In the news this week, how a comet smash could have kick-started life on Earth, are e-cigarettes safe, and why science and medical reporting in the media might be untrustworthy.
The Naked Scientists podcast is powered by ukfast.co.uk.
One of the biggest unanswered questions in science is how life began on Earth. One theory is that primitive chemicals developed the ability to copy themselves and eventually evolved to encase themselves inside bubbles, effectively becoming cells. And 4 billion years of evolution later, here we are. But where did those chemicals, which scientists think were early forms of the genetic letters or bases that make up our DNA, come from in the first place?
Well, this week, researchers have quite literally shed some light on the question by using a laser to recreate the conditions of a time when the early Earth was being brutally battered by droves of incoming asteroids and comets during a phase called the Late Heavy Bombardment. The energy in these collisions, they've shown, could have driven the chemical reactions that created DNA-like molecules, as science writer Mark Peplow explains.
A team of researchers from the Czech Republic has found that impacts from asteroids or comets billions of years ago could have created some of the key molecules necessary for life. As far as we know, all living things store their genetic blueprints in DNA. These blueprints are encoded in long sequences of just 4 different types of molecules, known as bases, which are peppered along DNA's backbone. Now, a related chemical called RNA, which many scientists think was the very first molecule to encode genetic information, that also uses 4 bases. They're called adenine, guanine, cytosine, and uracil. But the big question is, when life appeared on Earth, maybe about 4 billion years ago, where did it get these bases from?
So what are the current theories then about where those molecules might have come from in the first place?
Well, people have looked at the timing of when life arose, 3.5 to 4 billion years ago, and they've noticed that around about the same time, the planet was being absolutely hammered by comets and asteroids. And there have been suggestions that the space rocks could have delivered some of the molecules needed for life. What these Czech researchers have shown now is that the impact when a comet or asteroid landed could have synthesized the 4 crucial bases right here from ingredients that were already on the Earth.
Is that because as the impactor comes in and slams into the surface, it creates a whole bunch of conditions which are just right for the chemistry needed to make those molecules?
That's right. You're talking about temperatures in the thousands of degrees, intense pressures, as well as some ultraviolet and X-ray radiation. And the Czech researchers simulated that using a high-power laser to blast samples of a simple molecule called formamide, which is thought to be widespread on the early Earth. So you hit it with those conditions, it rips apart the formamide to create ammonia and cyanide in highly reactive forms called radicals. These then react further with more formamide to generate the 4 bases in RNA. And that's what they picked out of this mixture that they created in the laser furnace.
Where does the formamide come from in the first place, and what exactly is that?
Well, formamide is a very simple molecule. It contains carbon, hydrogen, oxygen, nitrogen, all those 4 key elements found in pretty much all the molecules of life. And it's what you would get when you're brewing up even smaller things like cyanide and water.
And so out in space, because the Earth obviously formed from dust and gas in space, there must have been some of this already there.
Yeah, you can imagine that if you have atoms of hydrogen, oxygen, nitrogen, carbon, these things being jumbled around as the Earth is forming, that is going to create simple organic molecules that are around the Earth at the time.
Do you think that a laser really can recreate what happens when a very big object hits the Earth?
So with all of these experiments, we can never really know how accurately they represent the conditions on the early Earth. There's always going to be a certain amount of supposition, speculation, but they can at least offer us clues about what are the most plausible explanations for the chemical origin of life. And with this laser experiment, because of the temperatures and pressures that they're creating, it's certainly going to, I mean, we know that temperatures and pressures like that were created during impacts during the late heavy bombardment, this period about 4 billion years ago. So we know those conditions were present on the early Earth. That's what makes this such a plausible suggestion.
Mark Peplow speaking with Chris Smith.
Phenomenal, isn't it, to think that that's actually potentially where DNA and RNA came from. Comet and asteroid impacts creating a bit of chemistry. Now, talking about amazing chemistry, over the past few years, the use of electronic or e-cigarettes has expanded massively, and this has sparked a passionate debate among scientists and health organisations and users about the safety and risks of these things, as well as their potential benefits in helping people to quit. But what is the scientific evidence for their safety, and who's using them? Kat Arney spoke to Robert West, who's Professor of Tobacco Research at University College London.
We know a lot about the concentration of the vapour that's coming from e-cigarettes, and the best estimate is that it's somewhere in the region of a 20th as harmful as cigarette smoke, which of course is extremely harmful. Not completely safe, but much safer than smoking. We know that the vast majority of people who are using e-cigarettes, certainly in countries like the UK, are smokers who are trying to stop or cut down. There are very, very few people who are never smokers or long-term ex-smokers using these products.
People who are concerned about e-cigarettes, they sort of broadly fall into two camps. There's almost the Father Ted style, oh, careful now. And then there's the people who go, well, look, these are much less harmful than cigarettes. We should just let people use them. We should encourage people to use them to get away from traditional cigarettes. Where do you kind of see these two camps dividing up?
I think one of the problems is that the two camps are coming from different moral positions. One camp is coming from what you might consider a utilitarian position, where you count deaths and you count harm, and you weigh it up and you try and formulate policies on the basis of which policy is going to cause the least harm or the most benefit. And the other camp, although they don't necessarily say this, that's my impression, is that they're coming from a much more absolutist stance, that tobacco industry is bad, nicotine is bad, smoking is bad, and it's all as bad as each other. What you tend to do is, once you start with a certain moral position, you tend to see the evidence in that way, and you tend to shape the evidence in that way. So the moralistic camp tend to exaggerate the harms of e-cigarettes and the potential dangers and downplay the potential benefits, and the other camp downplay the risks and actually potentially exaggerate the benefits. And it's a difficult job to try and find a path through this in terms of saying, well, what are the actual facts here?
As scientists, obviously, we should be basing our decisions on facts, and you would hope that health policymakers would base their decisions on facts. Do you think we have enough scientific evidence about e-cigarettes, or what more evidence do we need to gather before we can work out, are they safe, who should be using them, how should they be legislated for?
I think it's like any health policy decision. You collect data and then you formulate policy, and then you collect more data and you adjust policy. And so I think the policy approach that's being adopted by the English Department of Health and Public Health England is about right, which is to take a relatively cautious view, but also to recognise the potential benefits. So e-cigarettes, if they don't make a medicinal claim, can be manufactured and sold as a consumer product, but with restrictions, so that you can't sell it to people under 18, and there are restrictions on marketing. And you monitor, as we do, on a monthly basis what goes on, and you see how things are developing. That policy seems to be working quite well. We're tracking the smoking prevalence and the use of e-cigarettes on a monthly basis in England, and what we're finding is that prevalence continues to decline. Actually, quitting rates are higher now than they have been since we started tracking it back in 2007, so that's looking quite good. We're not seeing take-up of e-cigarettes among non-smokers. So far so good.
One of the things that people do get concerned about is, for example, we're now seeing adverts on the sides of buses for e-cigarettes that look for all the world like adverts for cigarettes. And a lot of big tobacco companies have now bought into e-cigarettes, and people are worried that it's maybe renormalising smoking after a lot of work to make smoking not look cool, to ban tobacco advertising.
There is a theoretical risk that the way that e-cigarettes are marketed, that they could be seen to renormalise smoking and to undermine all the work we've done on tobacco control. So we have to look at that. But one thing to remember about the tobacco industry is that they would like nothing more than for e-cigarettes to go away. And what better way of helping to make e-cigarettes go away than to do terrible things by e-cigarette companies and get the public health community to be anti-e-cigarettes. And then you have this accidental unholy alliance between the public health community and the tobacco industry, both achieving the common goal of making e-cigarettes disappear. The thing to remember is that the death toll from smoking is absolutely enormous and gigantic, and it's a catastrophe that continues on a daily basis, with 6 million people a year worldwide being killed by tobacco, people dying prematurely as a result of something that seems to be accepted within society. So we just have to remember what the challenge is here.
In Britain, it's a jumbo jet crash. Every day is the death toll just due to smoking. It's very high, isn't it? Katani was talking to Robert West about e-cigarettes and what they might or might not be able to contribute to quit rates.
Now, Ed Wilson has tweeted us at Naked Scientists about one of the stories we've been talking about so far today. And he said, energy of impact creating complex molecules is much more satisfying than trusting in creation in unknown conditions in space. It is nice to kind of have an idea of how it might all have started, isn't it?
Yes, indeed. And I thought it was very elegant the way that they would use an iodine laser to generate these 4,000 degrees C temperatures and then recreate the chemistry in a Petri dish that we think occurred in a comet crater. But these things are coming in at 20 kilometres a second. There's a lot of energy in there. And the key question, though, is where that formamide came from in the first place, because some critics of that story have said, would there have been enough of it around? Jury's out on that one. So we really need a bit more work on this. So we need to remain healthily sceptical. You're listening to The Naked Scientist with me, Chris Smith, and also with Ginny Smith. If you'd like to get in touch with us, the email address is chris@thenakedscientist.com. You can also pick us up on Twitter. It's @NakedScientist. Now, still to come, how universities are sexing up the science stories that they send to the media, and also a pill that will help you to fight the flab.
Before that, though, to the healing power of friendship. We all sometimes need a friend to help us through hard times, but that's not just the case for humans. A new study has shown that among our monkey cousins too, those with more friends are less stressed when times are tough, as University of Göttingen scientist Chris Young explains to Khalil Thurlaway.
Barbary macaques are one of a few primate species where we see strong affiliation between the males. So the males perform lots of friendly interactions with each other, they groom each other, socialize together. We wanted to try and examine exactly what benefits males are gaining from cooperating together. We know that long-term stress is bad for their well-being and their health. So if individuals can reduce their stress levels, this can help them greatly in their day-to-day lives, as they'll have a better overall immune function, a better overall health, and a better overall well-being.
How are you measuring the stress and the effect of the bonding?
We look at glucocorticoids, which is a hormone which is excreted or produced during stressful times. So the higher your levels of glucocorticoids, the higher your stress levels. So we collected fecal samples, which means that we don't have to capture the animals or anything like this. It's a natural method and non-invasive. We measure their social bonds through the rates at which they affiliate with each other. So how often they sit together or groom together, feed together, things like this. And then you have a proportion of individuals that socialize much less and ones that socialize much more. And we were interested in if those that have these strong social bonds that socialize the most gain stress-reducing benefits.
What were the stress-reducing benefits that you were noticing in these macaques?
Males lead quite a hectic life. Every day there are lots of events which are very stressful, so you can receive aggression from other individuals in the group. You can not get access to the best food sources, access to mating. And Morocco's a very cold place in the winter. In the summer it can be 40 degrees and bright sunshine and no shade. And then in the winter you can have sleet storms and snow and rain. So these were the two factors we really wanted to examine.
Has research been done in humans about this buffering effect? How closely related evolutionarily are macaques to humans?
Well, we split off quite a number of millions of years ago on the evolutionary ladder. But I think what the study shows is that what we see in modern day human society, where individuals who are very lonely tend to get a lot sicker and they have a shorter lifetime and often suffer from depression and things. And these things are all linked to having poor social relationships. Several studies have pointed to the fact that this might be alluded to modern society, where individuals are no longer in touch with their roots, and with things like modern technology, you no longer have to socialize and interact with other individuals. And I think what this study is showing is that this need, even in males, for social contact can actually come from much further back down the line. And having social contact with other individuals might have many benefits, which the virtual world might not be able to provide.
I guess in humans, there are easier ways to measure stress than going through fecal samples.
Yeah, human psychology is a bit easier to measure stress. They can conduct questionnaires and interviews with subjects, and obviously, unlike primates, they can respond and answer the questions. But there has been some research in humans, and they find that individuals who perceive themselves as being lonely or have fewer friends tend to cope less well in stressful situations, and they also live a shorter life and are more susceptible to diseases. Similar to what we find in our study, then, individuals with lower quality social relationships tend to do less well.
So close friendships really are very important in both your emotional health and your physical health.
Yeah, exactly. I think it's very nice to know that in times of need, keeping a few very good close companions, like we see in the Barbary macaques, is a very important thing.
Chris Young, and you know what they say, keep your friends close. And in the context of collecting faeces, your enemies closer. Ginny.
So now we're taking a behind-the-scenes look at how programmes like The Naked Scientists are made, and all the wonderful puns that go into them, as we hear about a study published this week on the relationship between scientists and the media. Researchers at Cardiff University have been looking at headlines and articles which can often have an impact on our daily lives.
Journalists often get the blame when scientific and health news is said to have been exaggerated or sexed up by the media. But this new study in the British Medical Journal has found that, in fact, the fault might lie with the universities themselves, with the finding that 40% of the press statements issued in 2011 by 20 top UK universities contained embellishments or overinterpretations of the original research. Petrock Sumner.
It's still the case that the majority of adults in the UK get most of their information about health and science from mainstream media sources. And so that's an awful lot of people, probably about 40 million people. This information is used so that it biases people's behaviour, and this can have a massive impact on public health. The government often run public health campaigns, but they will not have nearly the reach that just the daily media, both broadcast TV and radio and news, have on a daily basis.
And where does that information that populates the news, newspapers, TV broadcasts, radio shows, where does that news come from? How does it start life, and how does it end up in the hands of a journalist?
So a lot of it starts life with a published paper in the academic domain. So scientists who have done a study will try and publish their work in a recognised academic journal. And once that gets published, then the university or the journal can decide to issue what's called a press release, which means that they write a short summary and they send it out to journalists who then might or might not be interested in writing that story up in the news. And the press release is normally written by both the academic authors of the original research, but also specialised press officers who have experience in knowing how journalists like to receive information and not making it too long and making it accessible and so on.
And how reliable is the science, medicine, technology information that comes from these academic institutions and ends up in the public domain via this sort of route?
So it used to be assumed, and it's pretty common, to blame journalists when things go wrong in the press. So if you see an exaggeration or you see something taken out of context, it's often the case that their knee-jerk reaction is just to blame the journalist. But they haven't necessarily looked at the whole chain, and it turns out a lot of what the journalists say where they get accused of hyping or exaggerating, those statements are already present in the press releases. So the press releases haven't been careful enough, if you like, in the way that they've expressed things so as not to mislead and exaggerate.
How did you arrive at that conclusion?
So we studied all the press releases released by 20 major universities in the UK in 2011. And then we traced what was being said in the press release as well as in the news that followed the press release and what was originally said in the journal articles published by the academics.
And you were then able to compare the integrity of the message that reached the public
exactly.
with
so
what was in the journal.
Exactly. So we're able to see where the message changed and whether it changed most in the step from the journal to the press release, or whether it's changed most in the step from the press release to what actually got published in the news. And it turned out that the first step was actually the more changes and exaggerations were creeping in.
What sorts of things were being exaggerated? Can you give us some examples?
We analysed three types of thing. One was advice to readers to change behaviour. So one example was where the original journal article just made a fairly mild statement that if mothers want to breastfeed, they need more information. And then the press release went ahead and said mothers should breastfeed. Other examples that are quite common is where you have observational studies that don't necessarily provide evidence for cause. So, for example, if a study was done where people with higher cancer rates also ate more biscuits, that gets exaggerated into biscuits cause cancer.
Which, of course, they don't, just to reassure people, although potentially they might in some cases.
Yes, that was a hypothetical example.
To what extent does exaggeration reflect the fact that journalists might find it easier to flog a story to their editor and get it out there into the public domain if it's been sexed up?
We didn't actually find any evidence for that. It was quite surprising because, like everybody else, we went into the study assuming that hyped up press releases would generate more news. And in our study, they didn't. And we don't know the reason for that.
What's the scale of the exaggeration? If it's a little bit, it doesn't really matter, does it, so much? But is this pretty dramatic? Is there big numbers involved here?
So our study concentrates on the numbers rather than the scale. So we couldn't tell you whether any of these exaggerations are of the scale that would cause something like the MMR scandal to occur again. But the cumulative effect of so many of them that are happening week in, week out could have a very large effect just cumulatively because there's such large an audience and they're making so many health related decisions and there are so many news stories that break that the cumulative effect, although subtle for each individual or each individual story, could be quite large, either for good or for ill.
Do you think it's relevant that universities are now being ranked, not just in Britain but worldwide, by assessing how much news media they generate? So, for instance, if a scientist at a university publishes a groundbreaking paper and it generates headlines, that's being logged and used to rate that university. Therefore, is there potentially a little bit of pressure on press offices to generate as many headlines as they can? And therefore, there is something of an incentive for press officers, and maybe even scientists, to exaggerate.
Yes, I think there's more than a little bit of pressure. I think that we're in the early days of universities being held so much in competition and things like the news they generated meaning so much to them. At the moment, universities are very much thinking that the more news they get out there, the better. At some stage, there'll be so much news out there that it might reach saturation point, and then they'll care more about the quality and the accuracy and the reputation management in that news, rather than just getting news.
Petrock Sumner from Cardiff University with what amounts to quite a sobering message.
With the Christmas party season in full swing, some of us might be piling on the pounds after a bit of overindulgence. So wouldn't it be great if you could just pop a little pill that melts away all that unsightly flab? This week, scientists at the Harvard Stem Cell Institute announced the discovery of a drug that can turn white fat, the flabby stuff that stores energy and stops you fitting into your jeans, into healthier brown fat, which burns calories to generate heat. But, as researcher Chad Cowan explained to Kat Arney, it's not going to replace the benefits of a healthy diet and a bit of exercise anytime soon.
We had previously shown that we could make in a dish human white fat. It's the one that stores energy and that when we eat too much becomes in excess in obesity and then contributes to all the diseases we hear about, such as diabetes. We'd also made in a dish that other type of fat, brown fat, which actually burns off the energy content in the form of heat. And we'd done this using some genetic tricks, and we wondered whether we might be able to replace those genetic tricks with small molecule compounds, much like the ones that you find in pharmaceutical drugs. So we teamed up with a company, Roche Pharmaceuticals. Together with their team, we screened small molecules to ask, could we convert these white fat cells into brown fat cells? And we were very happy to discover that, in fact, 2 molecules from the screen that we did were very effective at changing the metabolic activity in the fat so that it resembled brown fat. So they still knew they were white fat cells, but instead of just storing energy, they became more metabolically active like brown fat cells and actually burned off that energy more readily.
Now, some of the coverage of this discovery has said this is a fat pill, you'll be able to pop it and the pounds will melt off. Obviously, that's probably an exaggeration. Where are you with these studies at the moment?
Yeah, that's definitely an exaggeration. This is early days. The compounds that we found, we've just begun to move into preclinical studies to see if we, in fact, treated them with the sort of doses that you might give would actually accomplish the metabolic change we would hope, which is maybe burning off fat or perhaps even prevent diabetes. Those experiments have really just begun, and we won't have an answer even from that phase of it for about another year. More encouraged by the fact that we've begun discussions with multiple companies about expanding this screen to find new compounds that might do this even more efficiently than the two we originally identified.
This does sound like the stuff of dreams. I'm someone who likes her cake. Do you think that it would even be a good thing to have a pill that you could pop that would alter your fat metabolism? Or would it be maybe only suitable for certain people?
That is my major reservation, because you don't want research like this to send the message that it's okay not to go to the gym or not to be physically active, because the benefits of physical activity are well beyond burning calories. It increases muscle mass, bone mass, improved mobility. There's so many benefits to exercise that a simple pill that's going to increase the metabolic activity of fat and reduce the caloric burden that we're all under is not the overall solution. I think it is a piece of the puzzle in our war against obesity, and it could probably help those people who have trouble being physically active to try to combat obesity. But it certainly should not be viewed as a cure-all.
What would be the effect of switching it from being these kind of storage fat cells to the kind of fat cells that create heat? Would you just get incredibly hot?
Some people estimate that if you had several grams more brown adipose tissue, your overall body temperature might run a little bit warmer, probably less than a degree, maybe half a degree, but even a degree or 2 degrees increase in body temperature could feel rather uncomfortable. We really won't know about the mean effect of this in terms of body temperature change until we complete our studies in mice. The hope would be that you could use this pill to convert some cells over to these more metabolically active cells. This is a relatively stable change, and then you could go off the medication for a certain amount of time and keep those cells working without a noticeable change in body temperature.
Wouldn't it be better to invest all the money that's going into this kind of research in just trying to get people to eat less cake and move a bit more?
I completely agree. Sadly, we've had 3 cures for obesity around for a very long time. You can exercise more, you can eat less, or you can get gastric bypass surgery. And unfortunately, none of the 3 are making a big dent in the problem. So I think if we just add more tools to our arsenal, I think that it could make a bigger difference in society and reducing our health burden. But I completely agree that making a bigger public push to making sure people are physically active and watch their diet is exactly the right approach in the long term.
Chad Cowan speaking with Kat Arney.
Just make the food harder to reach. That's the answer, isn't it? Put the fridge at the top of the stairs or something. Mark has got in touch by email, chris@nakedscientist.com. He says, I could do with a tablet to stop me enjoying food too much. When I have a cold, though, I do lose my appetite and then I lose weight. We also heard from Kev in Cambridge, who got in touch saying he would love to be a macaque monkey in the jungle because that would be a lot less stressful to be there in the first place. I can probably agree with you there, actually, Kev. You're listening to The Naked Scientists with Ginny Smith and also with me, Chris Smith.
On to our main topic for this week now, which is mass extinction. Humans often get the blame for wiping out species, and indeed our track record isn't very good. But species have been going extinct on a mass scale for millions of years. But why? Well, this week we're learning how scientists can use fossil evidence to wind back the clock and discover what makes things die out and what role humans might be playing in making history repeat itself.
In a minute, we'll learn what caused the mass extinctions that wiped out things like the dinosaurs. But before that, to find out more about the relationship between humans and mass extinction, we turn our eye to one particular example, and that's Australia. Australia used to look very different from the arid deserts that we see there today. It was more like the African savannah, and it was home to a range of huge animals, including giant kangaroos and giant koalas that were up to a third larger than their modern-day counterparts.
But fossils found in caves across Australia show that, around the same time that the first humans arrived, that's 60,000 years ago, these so-called giant megafauna disappeared. Gavin Prideaux studies these remains at Flinders University in Adelaide.
A lot of my research is based in caves right across southern Australia, and the reason for that is the preservation of the fossils in caves is exceptional. Caves are like a time capsule, very stable atmospheric conditions, and oftentimes caves open and close, so animals fall in or they're dragged in by predators, and then the caves seal up and then occasionally reopen again, allowing paleontologists to access these deposits. And then we get down essentially like archaeologists and excavate the different layers that contain the bones centimetre by centimetre.
How do you find the caves in the first place?
Well, we're utterly reliant on all the avid cavers out there who love crawling around in caves and discovering new caves. Well-meaning cavers will bring bones to our attention, kangaroo bones or cow bones or sheep bones or dog bones or whatever. But, 1 times out of 10, it's something really, really interesting. And that's exactly what happened, for example, with our discoveries in the Nullarbor caves. A group of cavers discovered in 2002, and then we subsequently went out there based on the photographs of the specimens that they took. South Central Australia is dominated by this vast treeless plain, the Nullarbor plain, which is Latin for no trees. There are thousands of caves, and on this one particular trip, a group of cavers discovered 3 caves with megafauna fossils in each of them. No one's found anything as good since out there in hundreds of caves that have been discovered, and no one had ever found anything before that. So it was an amazing discovery. And we've spent the last 12 years actually going out on trips out there and amassing a huge collection of remains that we're now wading through and studying to tell the story of how life changed in this area between 200,000 and 1 million years ago and before people arrive on the scene. Because once people are here in Australia, it's very difficult to tease the potential impacts of climate and the potential impact of human activities apart.
There are 2 phenomena going on then. You've got boom and bust, which happens in any population owing to natural climate change, and superimposed on that is an effect, if any, owing to the arrival of modern humans in Australia.
That's exactly right. And we've done similar studies in the southwest of Western Australia and similar studies at the World Heritage listed Maracoorte Caves in southeastern Australia. And what we see is that animal populations wax and wane with the coming and going of the ice ages over the last 500,000 years or so, but they don't go extinct. When we come to the late Pleistocene, let's say 50 or so thousand years ago, suddenly a whole range of species start to become extinct.
In other words, these are animals, they were there because they're in your caves and they can be dated to a point about 50,000 years ago, so they were around until then, and then suddenly they're not.
Exactly. As soon as we come to about 40,000 years ago, they're gone.
And that is also the time when we think the first wave of humans got down to Australia.
Exactly. And this is very strongly debated between the folks who believe the megafauna were driven to extinction by climate change, and when people say climate change in this context, they mean increased aridity, versus the impacts of people. And there's 2 ideas there for people. One is that people hunted them to extinction. Another one is that they lit fires and changed the nature of the vegetation that the big herbivores were actually utilising. That idea is sort of waning somewhat. The evidence is not borne out by the evidence of landscape burning, judging from the charcoal records. Obviously, the charcoal is representative of a bushfire, and we don't see a correlation increasing bushfire at about 50,000 years ago. So that idea is starting to wane. But, of course, one of the problems with the human hunting idea is that we don't have direct evidence. But then you can counter that by saying, well, if we go back and we look at the deeper geological record, the fossil record, and we see the persistence of several species through time, and then suddenly a new predatory animal arrives on the landscape, and then a lot of those species disappear. The simplest explanation is that the arrival of that new species had something to do with the loss of the others.
Can we use Australia then as a sort of case study of the influence of humans and apply it to other parts of the world?
It's an excellent case study because the timing of people arriving in Australia, it's probably going to emerge to have been about 60 or so thousand years. And so we've got a good record for the previous few 100,000 years of how the fauna are responding to climatic change in the absence of people. Then people arrive. We start to pick them up in the archaeological record, which species disappeared first, which ones hung around a little bit longer. And then, of course, Europeans arrive in Australia 200 years ago, and there's another massive spike in extinction. So in my view, there's basically 3 steps. You've had the initial megafaunal extinctions driven by hunting over probably a protracted period, 10, 20,000 years, by the first people who arrived in Australia, then very low level of extinction, then another increase maybe 6,000 or 7,000 years ago, and then a massive increase 200 years ago. What we're looking at here is evidence of a mass extinction for the first time, and of course it's becoming a worldwide phenomenon now, driven by a species. Every other extinction through history, the other 5 mass extinctions going right back to 540 million years ago, were driven by changes in the physical environment. An asteroid or comet hitting the Earth, volcanic activity. This example that we see in Australia is an excellent representative of this human-driven mass extinction that really marks the last 50,000 years on this planet.
And is still ongoing elsewhere in the world. Not a very good track record for us humans, is it? That was Gavin Prideaux from Flinders University, Adelaide, Australia.
Now, we heard from Gavin about a quite modern mass extinction and one almost certainly caused by humans. But modern humans have only been around for a relatively short time, just 60,000 years or so. And mass extinctions have been happening for much longer. So what else wipes out species? And how do scientists do a paleontological post-mortem to find out what happened? Sarah Shoston went behind the scenes at the Sedgwick Museum of Earth Sciences in Cambridge to meet dinosaur specialist Dave Norman. He explained what fossils can tell us about mass extinctions and why the dinosaurs disappeared abruptly about 60 million years ago.
Finding fossils like this remarkable jaw here, this is just a fragment of a jaw, and it's, 20 centimetres long, with sort of 7 or 8 centimetre long teeth, which are huge and spiked. I know that's a lizard because I'm enough of an anatomist to be able to recognise the characteristics of the bone, the shapes of the teeth. This is an animal that lived a long time ago, towards the end of the Cretaceous period, and I can say that it was lizard-like, but it had flippers instead of conventional legs, and it swam through the sea and was a giant predator. This isn't the world of the present day. This is a very different world. Studying fossils allows you to look at the way in which the world has changed and how different the world was in the past. Now, rather curiously, the animals that you find in rocks of Cretaceous age, about 65 million years ago, that particular population of types of animals, which included these giant lizard-like creatures, which are known as mosasaurs, and a whole variety of dinosaurs, very, very suddenly disappeared. And if you look at rocks that are younger than 65.5 million years of age, look as you might for these gigantic and dramatic looking creatures, you can't find any. Within 10 or so million years, you start to get rather different looking creatures, utterly unlike the ones that lived in that previous world. Life had changed, something very dramatic had happened that in a sense wiped away the mosasaurs, the dinosaurs, and indeed a whole variety of other sorts of organisms, in a sense made a space. It's like a punctuation in the history of life.
The world changed dramatically from a time of giant reptiles like the mosasaur with a jaw the size of my arm to the world we know where mammals and birds cover the land. What happened? Was it down to some cataclysmic event?
What we've got is, in a sense, a whole range of different lines of evidence that are all pointing towards something very dramatic happening about 65.5 million years ago. There were various hints from the fossils that animals disappeared rather dramatically about 65 million years ago and were replaced by different types of animals and plants. And therefore there was a lot of focus on rocks of exactly that sort of age and whether they have any particular chemical or geological characteristics. One of the things that started to be discovered was that the rocks at that time zone tended to have what are called tektites, lots of little glass beads in them, which could have been the result of an explosive event, rather like a hugely explosive volcano. Obviously, the nearer to this event, the more of these glassy beads you'd find, and the further away, the fewer you'd find. And the focus of attention gradually became southern North America and northern South America. And then some astrophysicists came along.
Luis Alvarez was an astrophysicist at this time. He was brought into this problem when his son asked him to help date a strange layer of clay from Panama. Often rocks can be dated using radioactive elements. These decay at a steady rate, so by measuring their relative abundances in the minerals in a rock, it's possible to work out the age of the rock. But this clay didn't have any minerals to date, so Alvarez suggested they look at the other elements in the clay. He found that there was an unusually large amount of the trace metal iridium. Iridium rains down on the Earth's surface at a constant rate, so any extra iridium could only come from one place: space. Geologists now had an idea of what to look for, and the glass speed distribution told them where to look. They took large boats off the coast of Central America, equipped with something like sonar for imaging the subsurface in what's called seismic profiling. There they found the key evidence and solved the mystery of the disappearing dinosaurs.
Finally, seismic profiling allowed us to identify a ring structure in the Yucatan Peninsula, and that ring structure seemed to reflect the fact that there was actually a very large meteorite impact that had left this huge crater under the ground, and that everything was now beginning to fall into place. We had this extraordinary coming together of evidence from an astrophysicist, evidence from the fossil record, evidence from the chemistry, the nature of the geological sediments of the time, which led to a sort of synthetic theory, which was, hey, the life on Earth at 65 million years ago was reset by an extraordinary event. And that this event was unpredictable, it was extraterrestrial in origin, and it's reset the way in which life has evolved on Earth.
Fascinating. Dave Norman from Cambridge University on his paleontological post-mortem of what wiped out the dinosaurs. And if you'd like to know more about how hidden fossils are revealed in rocks, you can listen to a special podcast we'll be putting out tomorrow featuring Sarah Finney, also from the Sedgwick Museum, and that's with Sarah Shostin, who you also heard in that piece.
So an asteroid was at least partly to blame for the dinosaurs' demise. But are giant rocks from space the only things that have threatened to wipe life off the face of the Earth? Before the dinosaurs even existed, there was a time when the planet was teeming with strange creatures in both the sea and on land, until disaster struck and nearly all of life died. Paul Wignall from the University of Leeds joins us to tell us about the biggest mass extinction in the history of life on Earth. So, Paul, how big are we talking here?
The biggest of all time, as you said. So we're looking at an interval of time when there was about 90% of all species, animals and plants disappeared.
That's a huge proportion, but do we have any idea of exactly how many creatures that would be?
It's difficult to say, but we're probably of the order of numbers of creatures would be millions, and number of species would be millions as well.
And when exactly did this happen?
What we call the end of the Permian period, and that's 252 million years ago, so a long time ago.
So that's quite early in the sort of history of life. I imagine the world would have looked very different back then.
Yes, it was indeed a long time ago. The animals on land were rather sort of primitive to us today. Lumbering creatures, primitive reptiles, and a group known as the therapsids, which have gone on to give rise to groups like the mammals, but back in those days, rather sort of sprawling posture.
And what about plants? Would the plants have been very different?
There was no sort of familiar flowering plants like we have now, but there was the conifers, fir trees and ferns and things like that were present then.
And in the sea, were things similar? Were there weird creatures there as well?
Again, in the sea, there was some groups which have now long gone, like the trilobites, which were familiar as fossils, but they are no longer with us. Other groups like fish and molluscs and various things like brachiopods, which are a group of little sort of shellfish, they were present and common in the sea then. So some of them we still have with us and others disappeared.
And trilobites, those ones that look like kind of giant woodlice, aren't they?
That's right, yeah, like little sea woodlice, yeah. But in other ways, it wouldn't be quite as strange as life on land would have looked.
So what happened to all these amazing creatures? Why did they die out?
Our number one culprit is this huge volcanic area in Siberia, which we know was erupted at exactly the time of the extinctions. Sort of that looks like the culprit, if you like, the large smoking gun for this catastrophe.
And how do you know that, A, that happened, and B, that was what wiped out life?
We know from dating it occurs exactly the time of the extinction.
And how do you go about dating things?
If you go to Siberia and you look at these lavas, they have layers of sediment in between the lavas, and you can collect fossils from those layers of sediment. And so you can look at the lavas and the fossils and look at the timing of everything. And you can give an actual sort of precise aid to the lavas by geologists use this technique called geochronologies, where you use radioactive elements and the rate at which they decay tell you how old rocks are.
Now, I can see how a volcano erupting in Siberia would kill off a lot of animals in Siberia, but how did that affect the rest of the world?
You're right. The actual lava was only dangerous in Siberia, but the main problem with large-scale volcanism are the gases that come out, and the gases are sort of rather familiar to us today, as well as carbon dioxide, which is a greenhouse gas, of course. And then we have other gases like sulfur dioxide and some acidic halogen gases as well, which all come out in huge amounts from giant-scale volcanic eruptions like this.
And would those gases have been directly poisoning animals?
Not directly. It's interesting, there's sort of a mixture of effects from that selection of gases. So, as we know with carbon dioxide, it's a greenhouse gas, so it causes climate warming, and we see good evidence for very rapid and very large-scale warming at this time. And the other gases have more of a sort of an acid rain effect and also may be able to damage the ozone shield of the planet.
So what would the animals have actually been dying of? Was it because it was getting too hot for them?
I think that's a definite role. Life in the oceans, we see at the time the oceans get very hot, they start to lose their oxygen, very bad for just about everything in the oceans. And on land, although it did get warm, I suspect it's the damage to the ozone shield, which is doing a lot of the main sort of stress for life on land.
So that would, of course, have meant that more UV could have got through, and that would have caused, things like cancers?
Yes, lots of cell damage, lots of plants will die. So if you eat plants, you're in trouble because the plants are struggling. The effects of very intense suntan, I guess, but too intense and for too long a time as well.
And do we know how bad the conditions really were? What sort of temperatures would it have been?
Extraordinary temperatures, actually. Recent results suggest that the ocean waters start to approach sort of high 30s, almost the sort of temperature that you have in the shower.
Wow, so that would make a big difference, I imagine.
It would. A shower lasts 5 minutes, but how to spend your entire life at that temperature is very hard indeed.
But not all life actually ended up dying out. What was special about the things that managed to survive?
Depends where you look. Certainly in the oceans, I think things that can survive high temperatures and low oxygen did very well. On land, I suspect a lot of the animals may have had this ability to estivate, which is the hot weather equivalent of hibernating. So when it gets just too harsh and too hot, maybe too arid as well, then you sort of sleep out those months and then just wake up when things might get better for a little while.
Could it happen again?
Could happen again. Yeah. There's been other events like this as well. This is just the worst one of its kind. I think we'll know if it happens because the magma rises up from deep within the Earth. People who can study the structure of the Earth would see it coming.
But even if we could see it coming, would there be anything we could do?
No.
Fairly worrying, but I guess we just have to keep our fingers crossed that it doesn't happen again in our lifetimes, at least.
I think so, yes. Yeah.
Thanks so much for your time. That was Paul Wignall from the University of Leeds.
Now, we've been hearing about mass extinctions, and Paul was just telling us about the Permian mass extinction, which was the biggest extinction event of all time when nearly all life died out. That was 250 million years ago. But could history repeat itself? Well, Mike Benton is a paleontologist from the University of Bristol. Hello, Mike.
Hello.
First of all, can we just look at one aspect which is an intriguing component of these die-offs, which is that every time we've had a mass extinction, the answer is that nearly all life disappears, but not all life. There's always something left. And what is it about the life that's left that means it doesn't disappear?
Well, of course, after an extinction event, the survivors, as Paul said, may be in some cases specially adapted to living in conditions of poor oxygen or high temperatures. In other cases, they're just lucky. And then it depends on what the physical conditions on the Earth are in the time after the extinction event. Often people have assumed that you have the stress, the impact of the meteorite, which did for the dinosaurs, or the massive volcanic eruptions and all of the consequences of that. And then the Earth kind of settles down rather quickly. Well, what we now know is, in some cases at least, after this big end Permian mass extinction that Paul was talking about, the Earth did not settle down. And for 5 million years, there were a number of repeated and rather similar crises. So as life picked up and got going again, certain groups started to speciate. Wham, they were hit again and set back. So it took about 10 million years in that case.
It really was survival of the fittest. What would have been the transition or the sorts of life that emerged as successors to what was wiped out during that Permian mass extinction?
In the early part, there were what we call sometimes disaster species. These are the ones that can take advantage of the rather stressful conditions in the immediate aftermath, as Paul was saying, species that can survive in conditions of high temperature or low oxygen. But then as the Earth settled down and sort of returned to equilibrium in some way, then you get the founders of the major new groups. And so we can now look back at that terrible extinction 252 million years ago and think, well, it actually punctuated the history of life and reset evolution by wiping out all of the previously dominant groups. So we can be glad, we're here, the dinosaurs came after that, various other groups were highly successful. But it did take a long time to recover.
I was going to say, is it actually this that helped to lay the groundwork for us coming along? Because I know that obviously mammals didn't really begin to dominate until after the dinosaurs had exited, but they had to come from somewhere. And were the ground rules sort of set out then with this mass extinction, enabling mammals to begin to appear?
It seems that may be the case because, as Paul said, there were a whole lot of different reptiles and so on at the end of the Permian, which were quite sprawling, awkward creatures, not very fast moving. After they had been wiped out, there was quite a change in pace in the following period of time called the Triassic. And the ancestors of mammals and indeed the ancestors of dinosaurs and various other groups got going. And they were no longer sprawling animals with the arms and legs out to the side. They kind of stood upright, as mammals do, birds do, and could move faster and adapt to other things, ultimately, including flight and various other modes of life.
So we effectively selected for animals that were much fitter, reproductively fitter, they were more adaptable, and if it hadn't been for these mass extinction events, then we wouldn't have species that are so resilient today, perhaps.
That might be. I think certainly there were stresses there. It'd be very wrong to think that there was a kind of inevitability or a kind of enhancement in a sort of mystical way. But in terms of evolution, the pace on land at least seemed to hot up. And maybe in the sea, because I think there were major steps in evolution of life in the sea. Faster moving fishes, which were the ancestors of the modern fishes that are very familiar to us in the oceans, from cod to sturgeon and all those types that they track back to then, and they were preyed upon by giant marine reptiles, which David Norman mentioned earlier. So there was a sort of pacing up all the way through.
One thing that's always baffled me is if you look at a crocodile, you've got there something which pretty much is reminiscent of what dinosaurs would have been sort of like, haven't you? They survived because the ancestors of crocodiles go back hundreds of millions of years. They weren't wiped out. So why did they persist? But these other stressors that did for the dinosaurs and things that came before them, why did crocodiles make it?
Very hard to say in any particular case, because whatever I say is untestable, so one has to be careful. Crocodiles and their ancestors have always been probably relatively low metabolic rate creatures, cold-blooded, we would say. There aren't very many species of them today. They were much more successful during the age of the dinosaurs. There were even bipedal two-legged crocodiles. There were even plant-eating crocodiles. So they were more adaptable then, it seems, than they are today. Whether it was something to do with that low metabolic rate, because we know pretty well that dinosaurs, in one way or another, were warm-blooded, a bit like birds, a bit like mammals today. Whether that meant that they needed larger food supplies, that's certainly something you would expect. Many of the dinosaurs, of course, were just positively huge, and being huge is not a great thing when the Earth is undergoing stress.
Because, of course, getting rid of that heat becomes a problem, doesn't it? Lastly, Mike, can you just tell us whether or not we might see history repeating itself? Do you think that there are other things coming now that means that it was the dinosaurs 60 million years ago, next it's humans?
I don't think we can specifically say that because the Earth has changed, and so responses to different kinds of environmental stresses may be different. But there's no question, as we heard earlier, that humans are now driving an extinction at quite a fast rate, and maybe 100 times the rate that it ought to be. Because extinction is normal, as I think you said before, species don't exist forever. But currently the rate of extinction is at least 100 times what it ought to be.
Well, I might have to take out a bigger insurance premium then. That's assuming the insurance company doesn't go down in the mass extinction too. Thank you very much, Mike Benton from Bristol, and thank you to our earlier contributors this week, Paul Wignall, Dave Norman and Gavin Prideaux.
And finally this week, Khalil Thurlaway has been busy tackling this earth-shattering question, sent in by John Stenson.
Where does the energy in the movement of tectonic plates come from? What causes them to move?
Fear not, John. I'm sure this is one we'll be able to crack. To dig up the answer, I spoke to Marion Holness from the Geology Department at the University of Cambridge.
So the Earth is divided up into an inner core, which is mostly made of iron, and then there's an outer silicate part, most of which is called the mantle, and then the crust is the skin that sits on top. Now the mantle is completely solid, but because the Earth's so hot inside, what that solid mantle does is convect, a bit like porridge in a pan on the stove.
Imagine you're making your morning porridge. It gets hottest at the bottom, because this is where the flame from the cooker is, right? It's the same with the Earth. It's hottest down at the core. As the bit of porridge at the bottom of the pan heats up, it rises to the top. As it gets further from the heat source, it cools and sinks back to the bottom. This circular motion is called convection, and there's a similar thing happening below our feet right now. And just like you get a crust on your porridge if you leave it, the Earth also gets a crust, except convection currents cause cracks. It's these cracks that are the boundaries of the plates, like giant islands floating on an ocean of hot rock.
It's a common misconception that the plates are actually being dragged along by the convecting mantle itself. That's not actually true. What happens during this convection is that you get mantle being dragged up at mid-ocean ridges, and that melts and makes new oceanic crust. And then at the other end, where you're destroying your oceanic crust, you're subducting it back into the Earth under its own weight. And what we're actually seeing is that the plates are being dragged along by gravity, pulling them back into the mantle at the subduction zones. So the kind of speeds that we're talking about for plate tectonics are essentially the same as the rate at which your fingernails grow.
Areas where plates collide are often areas with lots of earthquakes and volcanic activity. But where does this heat energy come from to move these giant bits of rocky crust?
So what's driving this? Why are the plates moving around? The Earth's mantle is convecting because it's so difficult to diffuse heat out of the Earth that it's easier to move the heat out by actually moving the Earth's mantle around.
All this heat is trying to get out because the Earth's core is so much hotter than the rest that the heat needs to even itself out. Heat always dissipates. This is why a cup of tea doesn't stay hot forever and will eventually cool to the same temperature as its surroundings. And the same process is happening here at Earth's core, except unlike your cup of tea, the Earth's core is around 6,000 degrees. But why is the centre of our planet so hot in the first place?
What's the source of this heat? Well, there are two sources. The first is the heat that's generated by radioactive decay within the Earth. And the second is primordial heat, which is heat which was present at the very formation of the Earth.
Earth. 4.5 billion years old and still hot. I hope our journey to the centre of the Earth has helped answer your question, John. And tune in next time when we take a healthy bite out of this question from Sarah Ward.
We're always told that we need vitamins and minerals in our diets, but I've been wondering what they really are. What happens to them when they get inside our bodies, if we can store them, and what happens if we don't get enough of them.
And if you'd like to speculate on why we need vitamins, you can email chris@thenakedscientist.com. You can find us on Facebook, tweet @nakedscientists, or you can join in the debate on our forum, which is at nakedscientist.com/forum. That's it for this week. We have run out of time. Thank you very much to Sarah Shoston and also Hannah Critchlow for production. Do join us next time for our Naked Scientist Christmas extravaganza. We're going to be electrifying the larynxes of a choir to find out how they sing. We'll make some fireballs at the dinner table with some festive Christmas chemistry. We explore why cracker jokes are, and often aren't, funny. And we show you that red wine really is good for you. Now, isn't that a good, positive health message? The Naked Scientist comes to you from Cambridge University. It's supported by the Wellcome Trust, the STFC and the EPSRC. I'm Chris Smith, and thank you very much for listening. Goodbye.